Thank you. Wow, all this chalk is bad. That's the best one. All right, so do make sure to get any exam regrade requests turned in today so that I can get them to Dr. Richardson. And we're more or less just going to get back in where we left off last time. So to kind of review the last thing we covered regarding what makes alkenes more stable than others, the second thing is going to be the substitution of the alkene. So a monosubstituted alkene is going to be less stable than a disubstituted alkene. Which is going to be less stable than a trisubstituted alkene. And then the most stable that we'll see is a tetrasubstituted alkene. So the reason for this increased stability as we increase substitution is that when we have these carbon-carbon bonds from the sp2 hybridized carbon to an sp3 hybridized carbon, the bond is going to be slightly shorter and slightly stronger. So for example, this alkene carbon-carbon bond is going to have a bond length of roughly 1.5 angstroms, where a normal sp3 carbon-carbon bond is going to have a bond length of 1.54 angstroms. So essentially, because it can form these tighter bonds between the two carbon atoms, as you increase the substitution of the alkenes, they in general become more stable. The third thing to consider when you're comparing the relative stability of alkenes is if it is a disubstituted alkene, if it is cis or trans substituted. So the reason for this The reason for this is because when you have a cis-substituted alkene, because you do not have free rotation about that double bond, it is effectively locked in a methyl-methyl eclipsed conformation. So if we think about what the Newman projection would look like for something like this, it's locked in that conformation, where the methyls are stuck eclipsing each other. Where with the transalkene, you still have an eclipsing interaction, but because the methyl groups are on opposite sides of the double bond, the energetic penalty for that eclipsing interaction is lower. So now we've more or less covered the gist of alkene stability. Is there any questions over alkene stability overall before we move on to actual reactions?
When you talk about the substitution what are you referring to?
Oh, by that I mean essentially the number of non-hydrogen substituents we have. Because on this one, every other substituent on the alkene is going to be a hydrogen.
So the less hydrogens you have on something, the more stable it is?
Yeah, or rather the more carbons you have on it, to think about it another way.
Can you write up the di-substitution, whatever words you can describe it on each of those little things that are greater than?
Sure. Any others? So let's think about it. So the cis has the methyl-methyl eclipsing interaction, and the methyl groups are larger than the hydrogens. So it's going to have a relatively large energetic penalty. When we think about the trans one, we still have an eclipse, but because the methyl is eclipsed with a hydrogen, the energetic penalty is lower, meaning that the transalkene is going to be more stable than the cis-alkene. Any others? Okay. So organic reactions. There's kind of two main ways we can display an organic reaction. The first and most simple one is the overall reaction scheme. And for an example of that, we can imagine this reaction with one propene with the acid hydrobromic acid to generate this product. And this is kind of the simplest way that we can represent a reaction. It goes into the lowest amount of detail. It tells us the least amount about what's actually happening. The second main way that we can think about a reaction, or at least display a reaction, is the mechanism. And this is going to essentially show us what each step in the reaction is, how we get from the starting materials to the products. It's also going to show the movement of electrons to show the breaking and forming of bonds as they happen. So taking the same reaction, what we're going to do is we're going to attack this proton on the hydrobromic acid with the alkene double bond. Keep in mind it is the pi electrons attacking, not the sigma. And then as we attack that, this is going to fill the bromine hydrogen sigma star localized on the hydrogen and break the bond towards the bromine. This generates what we know as a reactive intermediate. In general, intermediates are going to be pretty unstable and reasonably short-lived because they are going to be higher in energy than the starting materials or the products, so they're going to be more reactive. So then we're pretty much at the product that we showed in the overall reaction scheme. The only thing we have to do now is look at essentially what we have missing. From here we have a carbon that has an empty p orbital and a carbocation, and a bromine with a negative charge. And we know that to get from this intermediate to the product, we have to form a bond between that bromine and that carbon with the carbocation. So to do that, we're going to attack the empty p orbital on the carbocation with the negative charge on the bromine. And this will get us from the starting material to the product, showing essentially how the electrons moved every step of the way. Any questions about overall reaction schemes or mechanisms?
How would you know that you created an intermediate and that the electrons that go onto bromine don't immediately form that?
So essentially, you're asking how do we know it's not a one-step process to get from the starting material to the products? So we have empirical evidence for it, and we're going to get into essentially why we know this in a little bit. The reasons for that is we can hypothesize the existence of these intermediates based on the outcomes of the reactions of more complex substrates. So essentially, this is a very simple substrate that just goes through one intermediate to the product. But essentially, we're going to get into reactions with these alkenes where they rearrange in the intermediates. And because of that, we know that they must have gone through other intermediates based on the substitution of the starting materials and the products.
So at this point, without like prior knowledge,
Mm-hmm.
we have to be told that there's intermediate?
Can you repeat that?
At this point, would we be expected to know if something is immediate or if there's an intermediate?
So you'll be told every reaction that you're going to have to learn, and we're going to go through the mechanisms that we want you to know. So for example, at this point, we're just telling you that yes, it goes through a carbocation intermediate, and we can talk about kind of why we know that a little bit later on. Any others? Okay. So let's see. So with this just kind of introduction to how we can represent reactions, we're actually going to examine this reaction. And in general, for chapter 4, you're going to see a lot of reactions of this form called alkene addition reactions. So in general, an alkene addition reaction will take this form, where you start with an alkene, you react it with some species. To make it generic, I'm going to be showing you X bonded to Y, and you will end up with a product where the X atom is bonded to one of the atoms in the alkene, and the Y atom is bonded to the other atom in the alkene. And we have traded essentially this pi bond on the alkene for 2 sigma bonds to the various groups in this generic molecule. So the first one we're actually going to talk about, I've already shown you over there, which is the hydrogen halide addition to alkenes. So using the same substrate, we can have a molecule HX where X is going to be some halogen. So in this case, X will either equal fluorine, chlorine, bromine, or iodine. And any of these strong acids can do this reaction, but you're most likely to see it with chlorine through iodine. Just because when you see reactions later on, it's more synthetically useful to install one of these for, say, the substitution reactions you'll see in a couple weeks. So in general, we just add HX across the double bond there. So this reaction, when you have a similarly substituted substrate at both carbons, will proceed more or less like this to give you one product. But if the substitution at each carbon is differing, we encounter an example of regioselectivity, where essentially one site will be more likely to get one of the atoms in the HX than the other. So for example, using the substrate I showed initially to introduce reactions, we can show this reaction with HBr. And this one will give us majority this product, where the hydrogen was added to the less substituted of the two carbons in the alkene, and the bromine was added to the more substituted of the two carbons in the alkene. This is an observation known as Markovnikov's rule. So Markovnikov's rule more or less states that if you're doing an addition reaction to an alkene, the non-hydrogen atom will go to the more substituted carbon in the alkene.
What is more substituted mean?
So more substituted means that it has more non-hydrogen substituents. So in this case with propene, the carbon in the middle is the more substituted carbon because it is bonded to a carbon and a hydrogen, where the terminal atom in the alkene is just bonded to two hydrogens. Any other questions?
Sorry. So what you just said. So it's another way of looking at it, like the most substituted is the one that's bonded to the most H.
The most substituted has the least hydrogen substituents on it. So again, this is the most substituted carbon because it has fewer hydrogens than the other carbon in the alkene. Exactly. So for example, this one's symmetric, so it doesn't matter which atom it goes to. You'll end up with the same product in either case. But if we have an unsymmetric alkene like this one, then you'll end up with a mixture of products. So if we expose this alkene to the same reaction conditions, we end up with a roughly even mixture of products. Because both carbons in the alkene have equivalent substitution, which means that neither carbon is more or less likely to get the bromine in the reaction. Any questions about anything so far?
Will the halide always break the double bond?
So this acid will in general react with the double bond. And we'll talk about the mechanistic details here in just a minute. So in general, when we react these alkenes with an acid, as I said before, it's going to go through a carbocation intermediate. And that carbocation intermediate is going to dictate essentially where the bromine ends up. So if we want to think about the mechanism for this example below, we're going to have the pi electrons again attack the carbon, the hydrogen bromine sigma star, which breaks the hydrogen bromine bond heterolytically towards the bromine. and then it forms a carbocation at that position. We could imagine it forming the carbocation at the other position. But it turns out that the more substituted carbocation, just like more substituted alkenes, are more stable. Although the rationale is a little different. So when this alkene reacts with the HBr, it generates a trigonoplanar carbocation intermediate, which is sp2 hybridized, and has an empty p orbital. So the reason that the more substituted carbocation is going to be more stable is that if we have a carbon adjacent to the carbocation, its carbon-hydrogen bonds can donate some electron density to the electron deficiency on the carbocation. One way that you can kind of think about this is with a bond-no bond resonance structure, where we have the carbocation there. We can imagine a resonance structure like this. Where that positive charge on the carbocation is somewhat delocalized. Now, it's not a full resonance structure. We don't actually consider it having the bond broken, but this is a way to help think about why greater substitution at the carbocation gives you a more stable carbocation. So just like the trends with alkene stability, we have a similar trend with carbocation stability. Where a methyl cation is going to be the least stable carbocation that we can end up with because we have no carbon groups adjacent to donate electron density from their carbon-hydrogen bonds. So next in stability, more stable than a methyl carbocation is going to be a primary carbocation, where we have one group over here which is able to donate into the empty p orbital to help stabilize it to some extent. After a primary carbocation, a secondary carbocation is going to be more stable, just following the trend, because now we have more carbon atoms that can donate electron density through their carbon-hydrogen bonds to the electron deficiency on the carbocation. And just following from this, a tertiary carbocation is going to be the most stable for the same reasons. Now we have 3 different methyl groups that we can donate electron density from the carbon-hydrogen bonds on them to the carbocation. Yeah, so this is primary, secondary, primary carbocation.
So I understand that they can share electron density with their substituted neighbors, but what happens if it's like a superpolar bond, for example, between carbon and fluorine, where fluorine doesn't have any hydrogens that want to donate electron density, and the fluorine's actually pulling even more electrons away from that carbon?
So then things get a little bit tricky. It's going to make it harder to form the carbocation because it's going to make it even more electron deficient.
So in that case, would it be more stable for the methyl to form a carbocation?
It's going to be hard to make the distinction at that point. Any others? Okay. So because of this difference in stability, the alkene addition reactions above can get a little more complicated. So for example, if we had this substrate and we reacted this with HBr, out of the two possible carbocations that we can form from this attack, it's going to form the initially most stable one. So it'll form the secondary over the primary carbocation.
What does it do?
So there's two possible carbocations that this can form when it reacts with this proton on the HBr. And it's going to form the more stable initial carbocation. So for example, the other possible carbocation this one could form would be a primary. And given that we have these two options, it's going to choose the more stable one over the less stable one.
Why does it not form a carbocation on the third carbon?
So initially it can't because we have to involve the carbons that are only involved in the pi bond. Because remember, the electrons that are actually attacking the proton on the HBr are the pi electrons in the pi bond, which means when we form a new bond to something in the molecule, it has to be one of the carbons that was involved in the alkene initially. Any others? Okay. So after forming the initially most stable carbocation, and I'll cross the less stable one out just so we know, it's actually going to rearrange. So you're onto something in that we could form a more stable carbocation in this molecule. It's just it can't form it immediately. We have to go through this intermediate and then have a 1,2 hydride shift. Where essentially we move this hydrogen and its electrons over to this carbon, which moves where we have the carbocation. So now, after having gone through the secondary carbocation, the molecule rearranges through a 1,2 hydride shift to generate a tertiary carbocation, which is an energetically favorable reaction because the tertiary carbocation is going to be lower in energy than the secondary. And then at this point in the reaction, the bromide ion is going to attack the carbocation to give us this as the major product. Any questions so far? Uh-huh.
What's stopping the bromine from attacking the secondary?
So that's a good question. The answer comes down to relative rates. So because we have to consider, if we think back to just kind of general kinetics and the rate laws, we have to consider both the concentration of the bromide ion and the carbocation to get the bromine to attack there. But the reaction to go from this secondary carbocation to the tertiary carbocation only relies on that rate because we don't care about the concentration of two species. So in general, intramolecular reaction steps are going to be faster than intermolecular reaction steps just because you don't have to worry about the concentration of two different species. Any others? Okay. So a hydride is not the only group that we can have migrate to generate a more stable carbocation. If we take a similar substrate to what we looked at just a minute ago, and react it with HBr to generate a carbocation, we come to this intermediate. So now in this molecule, we don't have a way to do a hydride shift because we have a terp-butyl group over here, and that carbon has no hydrogens on it. So in this case, to generate a more stable carbocation, instead of having a hydride shift, we will have a methyl shift. So just like the hydride shift, the methyl group is going to take its electrons with it and move over to the adjacent carbon. This will generate for us a tertiary carbocation. And the methyl group that was once there has now migrated to the adjacent atom. And then at this point in the reaction, the bromide can once again attack, generating our product. So a methyl group, we can essentially shift any alkyl group to a neighboring carbocation to generate a more stable one.
Why don't you draw the bromine ion in the second or in the first intermediate step?
I mean, we can, but it's not participating in that mechanistic step, so I left it out. It's still hanging out there. It's not gone anywhere, but because it wasn't involved in the actual step, I left it out.
Okay.
Other questions? Uh-huh. Methyl shift. So where this one was a 1,2 hydride shift, this is a 1,2 methyl shift.
Where does the 1,2 come from?
So this gets into nomenclature for pericyclic reactions, which you don't really have to worry about for this course or organic 2. But if you want to know, it's because we have a essentially one atom unit moving across 2 atoms. So the 1 is this methyl, and then the 2 that it's moving across are the 2 atoms in the chain. Any others? Uh-huh.
So could you speak to how we can get something that has like a molecular weight of 15 that's tightly bonded by a sigma bond where the electrons are perfectly matched to a carbon with a positive?
So it's because this process is energetically downhill. This is going to be a relatively high energy intermediate because we have a secondary carbocation. If we can rearrange to make a tertiary carbocation, it's going to be energetically favorable. And I mean, you're right that this carbon-carbon bond is relatively strong, but because we have that carbocation there, it's going to weaken the neighboring bonds that are donating into it, which makes the transfer a little more facile. Other questions? Okay. So in addition to a methyl shift, we could have a similar thing happen where instead of a methyl migrating, we could move an ethyl group. And then at that point, the bromide would attack, giving us our alkyl halide. So in general, if you have multiple groups that can migrate, the smaller of the groups is more likely to migrate. So for this one, although I've shown the ethyl group as the group that's migrating, the methyl is more likely to migrate in this example. The only kind of caveat to that is if we have a good energetic reason to migrate a heavier group over, say, a hydride or a methyl. Sure, don't mess anything up. A good example of that would be this molecule right here. So if we take the first step of the reaction again, and generate a secondary carbocation, we could at this point just have a 1,2 hydride shift happen to generate a tertiary carbocation at that carbon right there. However, because we have a 5-membered ring adjacent to a carbocation, and 6-membered rings are more stable than 5-membered rings due to having a better bond angle for them and fewer steric interactions, we're actually going to migrate this ring and basically make the ring 1 atom larger. So it's a little hard to keep track of where every carbon goes when you're doing this, so I'm going to go ahead and number them. So we're going to break the bond between carbons 2 and 6, and we're going to form a new bond between carbon 6 and carbon 1, meaning that we're going to end up with the carbocation on the atom we broke the bond from, which is going to be carbon 2. Let's see. And a methyl group there. Do you have a question?
Yeah, are these all 1,2 methyl shift, or is that, what are the?
So these are in general all 1,2 shifts. Whether it's a methyl or an ethyl or a hydride depends on the group that's migrating.
So in the second example, what would that be?
It's a little easier just to call this one a 1,2 alkyl shift and just leave it more generic.
Okay, and then for the one that we're doing right now, is that also?
Yeah, this is also just another example of an alkyl shift. So this is an example of where, because we have another energetic benefit that we can take advantage of, instead of just doing the simple hydride shift, this ring is going to expand to take a lower energy 6-membered ring over the previous 5-membered ring. But it's not done rearranging. We still have a tertiary carbon right next to a carbocation, so it can continue to rearrange. Now at this point, we can generate the most stable carbocation. That looks like an A. Where we've gone from the secondary to the tertiary carbocation. And then at this point, the nucleophile, in this case iodine, will attack the carbocation to give us this product. Any questions about anything we've seen so far? Uh-huh.
How important is it to draw the hydrogen, the final step?
It's not that important. It's basically just there so to keep track of all the atoms while I'm explaining it. If you're fine omitting it and that won't cause any mistakes, feel free. Any other questions? Okay. So similarly to how conjugation can stabilize a conjugate base when you're thinking about acid-base chemistry, conjugation can also stabilize a carbocation. For example, a tertiary carbocation is going to be the most stable aliphatic, unconjugated carbocation that we can make, but it's still going to be less stable than a primary alkyl. The reason for this is just like for acid-base chemistry, where when we have a conjugate base that is conjugated, we can delocalize the negative charge over more of the molecule. Here we can do the exact same thing. Because we have these pi bonds that can delocalize the positive charge, the carbocation is going to be much more stable than an aliphatic carbocation would be. Following the trend, if we add more conjugation to the carbocation, it's going to be further stabilized. So if we have, say, a phenyl ring that the carbocation is conjugated to, yes? Oh, so conjugation, basically being able to draw resonance structures where we delocalize the charge over a larger portion of the molecule. So for example, I can draw a resonance structure for this one that delocalizes that positive charge into the ring, where with the arrows that I've drawn, we can go to this resonance structure right here. And because of these various resonance structures, in other words, different locations we can put the positive charge, it's going to overall stabilize the carbocation. Any other questions? Okay. So this can come in play when you're actually doing reactions on these substrates as well. So if we took a alkene like this, and subjected it to the reaction conditions that we've been thinking about, so this time HCl, we have essentially a secondary carbon at both of these positions, but one of these positions is going to generate a more stable carbocation than the other. So when we generate the carbocation from this starting material, there are two options. There's the one farther away from the benzene ring, and then there's the one right next to it. So in this case, we're going to selectively generate the benzylic carbocation because this carbocation is going to be drastically more stable than if it were on the other carbon due to the conjugation into the ring. So even though both carbons were both secondary before generating the carbocation, the one with conjugation is going to be preferred. Any questions about that? Uh-huh.
Just to clarify, conjugation is just resonance?
Yeah. Any others? Uh-huh.
What's stopping that positive charge from going into the benzene ring and then that chlorine combining with those? Are they all likely products of this reaction?
So in this case, this is going to be the most likely site of attack. The reason being due to an effect called aromaticity, which you will cover a little bit later. You might have already seen the consequences of it when taking NMRs. Essentially, an alkene will have a chemical shift of like 4 to 6, but because we have an aromatic ring, aromatic protons are going to be roughly 7 to 8. And that's because aromatic molecules enjoy a greater stabilization due to the increased conjugation in there, as well as, what's the word I'm looking for? Just kind of the nature of aromaticity, where essentially if you have the correct number of electrons in a cyclic array, it's going to be more stable than it would be otherwise if you just had in a linear conjugated system. Any other questions? Uh-huh.
Why can the cation not form on the other side of that bond? Like, what makes that place for the cation more stable?
So if we consider both options, this one's just a normal secondary carbocation. But this one is stabilized through resonance being next to that ring there, because we can draw resonance structures that delocalize the charge. And because we can delocalize that charge, it's going to make that carbocation a lower energy carbocation than the unresonance stabilized one would be. Any others? Okay. So let's try to cover the last thing for today. I'm going to talk about essentially these reaction coordinate energy diagrams, which is another way to kind of think about each individual step in a reaction. So taking the first reaction, the first halohydrogen addition to an alkene that we looked at, we can consider the energy levels of every species in the reaction and essentially why things go the way they do. So where this y-axis is energy, the x-axis is reaction coordinate. So starting from the starting materials, we have an activation energy to get to our first intermediate, which we know is the carbocation. So we can, in a reaction coordinate energy diagram, we can, So it's essentially the progress of the reaction as it proceeds, working from the starting materials to the eventual product. So we can notate the intermediates with the notation I star to notate that it is an intermediate in the reaction. It's not the product that we isolate, but it is something that forms along the way. Between that, though, is what's known as the transition state. And this transition state is kind of a hypothetical intermediate between the starting material and the first reaction intermediate. This is going to be a relatively high energy state, and we notate it with TS double dagger. So in general, when we're at a transition state, we're in the process of breaking and forming new bonds, which means that any charges that we're generating in the intermediate are going to be starting to form. So for example, we're going to generate a positive charge on the carbon that becomes the carbocation. So we have a partial positive beginning to generate in the transition state. And because we end up with a bromide ion, anion, it is going to start generating a partial negative charge on it, as well as the carbon-carbon pi bond beginning to break, the hydrogen-bromine sigma bond beginning to break, and this new carbon-hydrogen sigma bond beginning to form. Any questions about any of this so far?
Can you make out what's in the transition state?
Oh, it's delta, lowercase delta.
Okay, so that's delta negative to the bromine, delta positive to the carbon.
Yeah. Any others? Okay.
What is up to the right outside of the...
That's TS double dagger. That's the nomenclature. That's how we can notate that this is a transition state in the reaction. So as we proceed through the reaction, let's see, where is she budget? Yeah, they're about the same. We go from the intermediate species to our final product, which is going to be this alkyl halide species. So this will go through yet another transition state where we begin to form the bond between that carbon and that bromine. So when we look at these kind of diagrams, these reaction coordinate energy diagrams, there's some information that they can tell us about how fast each individual step is. And essentially what is going to tell us that is the relative size of the hump that it goes over to get from one species to another in the reaction. So if we're only considering the forward reaction, we have two different activation energies, which can be referred to as delta G double dagger. And the larger of the delta G double daggers is going to dictate which step is faster than the other. So basically, because we have a very large barrier to generate the carbocation intermediate, because carbocations are pretty unstable species, this first step in the reaction is going to be what's known as the rate determining step. So when you're thinking about the actual rate for this entire reaction, it is more or less governed by just the rate of the first step. Because the barrier for the second step is so much smaller than the barrier for the first step, the second step is going to happen a lot faster. So we only really care about, as far as the rate of the reaction goes, the first step in the reaction for these. Any last questions? Huh? Yeah, so it includes the enthalpy and the entropy.
Up there
Yeah.
with the shift.
Uh-huh.
Once you break the double bond, wouldn't
Yeah.
the hydrogen be on the end of the one?
The hydrogen is going to be at the end of the carbon right to the right of the one.
Yeah.
Yeah.
Yeah. So then how does that then end up over here in this step?
That's a different hydrogen.
Oh, it is?
Yeah.
Okay, so there's still a hydrogen up
Yeah.
here.
That one still got added.
Okay.
It's just that we're not showing it at that point because it's implied by the skeletal structure.
Gotcha. Okay, that makes a lot more sense. Thank you.
No problem. Thank you.